full disk view. And now, as in beautiful partnership, ICON is going to come along and provide that those in situ measurements, sort of flying right through some of those plasma bubbles that we've been imaging with gold for nearly a year now, and also the remote sensing of looking right down through the ionosphere at all of these different layers. And so it's a wonderful partnership that we're going to have. And of course, then looking forward to the future, we're launching in a few years a gravity wave experiment that's going to go up called OR, that's going to go on the ISS, and looking a little bit further forward to geospace dynamics constellation. And so we're really excited about all of these missions coming online and really telling us about this protective layer. It's the top of our atmosphere. So it's our frontier with space.
I just would second that. I think that gold is a great asset for ICON. In fact, if you show the movie again, it shows the correspondence. What we finally have for space weather is a geosynchronous observation coordinated with a in situ observation or something very close up. So we're looking at space weather like happens with hurricanes, where the GOES satellites provide large scale imaging, and we actually fly airplanes into the hurricanes to sample them and to gain more information. And that's what ICON and GOLD are going to be able to combine to do for space weather.
So take us deeper into the spacecraft and how all of these parts are going to work together, and then we might go after that to Steve to also talk about how Northrop Grumman brought this into fruition.
Well, I'll just talk just about the instruments, and I'll let Steve talk about the spacecraft. So we have an image of the spacecraft, the observatory, as we say, which is now the payload for the Pegasus, wrapped up and ready to go before the fairing goes on the Pegasus. You can see the solar panels wrapped around it. Those unfurl and give us the power. But the instruments are there exposed at the top, and those instruments will be on the bottom side of the spacecraft, always pointed down. This image shows those instruments very much more clearly with the solar panels removed. We are connected, and we put that payload together, which is at the top, and we pass it off to Northrop, and who did the rest of the work to build up the observatory.
Great. Thanks, Tom. Hey, first off, I'd just like to thank you and the whole team at UC Berkeley, and especially Bill Craig, the program manager, who just the leadership and the exceptional drive to get this program completed was really exceptional. So thank you for that. And also, Nikki, the team at NASA headquarters, the support in the Helio director and also at SMD, just the support for the mission has really been exceptional. And the guidance that we navigated through some of the shoals has been really exceptional. So thank you for that. And then I'd be remiss if I didn't thank the Explorer's Office as well, and also all of the team at NASA Goddard Space Flight Center for the technical support and all the technical expertise. So if we can go back to the image, please, of the spacecraft. We at Northrop Grumman are extremely proud of the ICON mission and the success we've had in developing that. It really builds on a 35-year, thank you, a 35-year legacy of success and providing successful missions to both NASA and the science community. The ICON mission is based on what we call our LeoStar 2 spacecraft bus. It's kind of the workhorse for the small and mid-sized Explorer missions. And the latest instantiation of that was the TESS mission, which launched from the Cape in April of last year. And that is finding exoplanets to this day and really is doing exceptionally well in terms of mission utility and overall value. And the LeoStar 2 bus really is a high-value, high-capability bus for the ICON mission. If you start at the bottom, Tom had mentioned the instrument suite on top. The bottom is what we call the spacecraft bus, and that provides the attitude control, the stability, the positioning, the pointing for the instruments to make sure that we get maximum science utility. Also, Tom mentioned the solar arrays, and they're much like the solar arrays most folks have on their houses these days. Photovoltaically, they take the solar energy, convert it to current energy that powers the spacecraft and allows the spacecraft to function. And then also there's a master computer that controls the spacecraft and really does all the functionality, if you will, and in addition to the S-band communication links, which allow us to collect data, downlink it, and also upload commands from the ground. So really, it's a really compact science platform. It's about the size and the mass, weight, if you will, of your refrigerator at home, with much more functionality, of course. And the spacecraft, as Tom mentioned, started with the spacecraft bus, integrated all of the 4 instruments, which then became the observatory. And that has been thoroughly tested, verified, and certified. And I'm happy to report that we're now a go for launch. And provided the weather is successful tomorrow, this will be the 9th mission that Northrop Grumman has provided the full turnkey solution to. And by that I mean both the spacecraft, the instrument integration, the full certification, and then the launch services as well. So we're looking forward to it. The team's energized and excited, both here at the Cape and also at UC Berkeley in the Mission Control Center. And I look forward to tomorrow evening.
Fantastic. We're about to go to questions in the room and from the phones, but we're going to have one last question up here, which is, Nikki, you've talked about overseeing this large heliophysics portfolio. Give us just even another step back about how all of this fits together.
Yeah, so I've got to say being the Heliophysics Division Director is fabulous because I have spacecraft in all these incredibly important key locations. Obviously, Parker Solar Probe launching last year in August, up there in the corona, telling us everything that's happening with our star. And the important thing, of course, is what that is doing to us here at Earth and indeed shaping our very sort of protective bubble that we travel around the Milky Way in. And so, we have Voyager all the way out there, but we have all these key locations really covered well. Both ICON and as Tom mentioned, ICON and GOAL working together will be providing new measurements for us to put into our space weather models, which is going to make transformational improvements in our ability to predict space weather, thereby protecting our assets and our astronauts in space. But I have to say, it is a great time to be a heliophysicist. But to wrap up, go Pegasus, go ICON.
Fantastic. Thank you. We will take questions from the room for starters. Marcia, yes, please.
Marcia Dunn, Associated Press, probably for Nikki. The mission is 2 years late, and I'm wondering, has the mission evolved scientifically during that time? Have you tweaked the instruments, added new purpose, whatever, any changes in that regard? And also the latest mission cost, if you could review that too.
So we haven't changed any of the instruments. The instruments are still perfect and just as they were designed. I have to say, yes, it has been a 2-year delay. We have learned a little bit more science. We now have a year's worth of gold images. And so I think, if anything, we're a little more excited about what ICON is going to bring to us. No changes to the design of the spacecraft or the instruments at all, but just a little bit more excitement in the science. Can you do the mission cost?
I can't, but I do know that it is still not over. We have not discovered it to be over what it was supposed to be.
So despite the delay, that it did not exceed the budget?
It is still within its agency commitment.
And we can
cost,
get you
yes.
the number
And I
for
can
sure
get you the
afterwards.
number. Yes.
All right, the gentleman behind.
Hi, Stephen Clark from Spaceflight Now. Maybe Tom or Nikki can talk about how observations from ICON may help space weather prediction going forward, specifically in forecasting versus just learning how the plasma lab works.
Yeah, so it really is benefiting the modeling. I mean, obviously, when you fly through these new regions, you're getting new information and you start to understand the science much better. But specifically for the space weather, we have these models that go all the way from the sun right the way down to the mud. And, we want to be able to make sure we're putting the right physics in. And so by getting this understanding of what is going on, how the terrestrial weather and the space weather are mixing together, you put exactly the right physics in those models, and then you can drive them with, you now know what's happening at the sun with Parker Solar Probe. You can drive those models using the solar data, and you now have a much more accurate prediction of what that solar wind is going to be driving in this region. Tom, would you like to add?
Well, I mean, space weather, we think of it as like a really large solar flare creates a CME that arrives at Earth and causes a lot of disruption. But that's a space storm. Space weather is how all the changes from one day to the next that occur in the ionosphere. And as we discussed, we thought that would be sort of not that exciting. But near the equator, around the equator where the plasma is densest, that changes drastically from one day to the next, which implies that there's changes in the winds from one day to the next, the background wind that is pushing the plasma this way or that way. And that's not built into any of our capabilities or models for prediction right now. So if we actually see the wind blowing east one day and west the other, that will be a surprising result in and of itself. And we're measuring the effects of those winds immediately. So, there are sun to mud models that are trying to capture this capability of capturing really, if there's something going on in the Midwest, some large storm front that generates something higher. But those have really never been verified. So we're going to be looking at those kinds of things to understand the day-to-day changes in the ionosphere that we can't predict right now.
I just want to do a quick go back to Marsha's question, because I did forget to say one thing, which is I did actually want to do a shout out to the whole team who actually used the most recent couple of months to do a complete test of the observatory to make sure everything was still working. I know sometimes when you think 2 years, you think it's just sat there. No, they exercised they put out the solar panels, they exercised all of the motors. And so it was a really, really beautiful partnership between Northrop Grumman and Berkeley and all of that team that really stood up. And thank you to LSP for letting us do it also. So just wanted to do that.
Sure, and I would just add to that that during that hiatus period, the spacecraft was kept under a constant dry nitrogen purge, kept it not only clean but also extremely dry, so they didn't have any issues with moisture incursion or any other things that might affect the overall electronics capability. And to Nikki's point, yeah, we did a full, what's called a comprehensive performance test, a CPT, to exercise all the main elements of the spacecraft, all the software. And then one of the key concerns with the extended period of storage was the potential for a solar array hiccup, if you will, during deployment. We deployed the solar array and it went extremely well, no issues, everything's nominal, and we have a very, very high level of confidence for tomorrow.
Ken.
Ken Kramer, Rocket STEM and Space Up Close. Actually, one of my questions was exactly this, about what you've done to make sure the spacecraft is still operating well. So did you find anything that you had to replace?
No, everything was nominal. I mean, there was a couple minor hiccups, some learning, if you will, but nothing that was out of family. And again, my main concern personally was the solar array with the 5-panel deployment and the extended 9-minute and 10-second deployment sequence. Any minor perturbation would certainly be, I'll say, catastrophic, but no issues, and everything was nominal.
Okay, great. And the science question I have, you mentioned the ISS is in the ionosphere. Is it making any measurements right now? And you might have mentioned an instrument's going up there soon. Can you talk a little bit more detail about that?
Yeah, so there's an instrument that'll launch, I think, 2023, but yeah, thank you. And it's actually, it's picked from our Explorer line. It's a mission of opportunity. It's going up on the ISS, and it is a gravity wave measurement. So it's going to be, again, looking down, doing these big sort of sweeps through the different layers of the ionosphere. And so, yet another really important measurement for us to add to our IT science. But today is all about ICON.
Right, but there's no ionospheric measurements on the ISS made today. Is that right?
That is correct. We don't have any particular ones. We do have CubeSats, of course, that are measuring the ionosphere in the IT system, but from the ISS, other than all of the cameras, you saw all those beautiful images, they're all taken from the ISS.
All right, thank you.
This gentleman here. And then we'll have one question from the phones after that.
Jim Siegel, I'm with Spaceflight Insider. A question for Nikki, I believe. The altitude of this ICON satellite is going to be about 360 miles or so, I understand. So could you provide to my viewers a little bit about the context of that altitude compared to, for example, the different zones in the ionosphere? What other satellites are up there in that region? Also, with respect to satellites that the ionosphere might interfere with, like all of those up in geosynchronous orbit, or 22,000 miles. So could you give us a sense of those distances from the Earth?
Actually, that was your graphic, if you'd like to.
I could try to answer the question. So, speaking, this orbit is has about a 15-year lifetime at that altitude. Your naturally atmosphere drags and slowly slows you down. So not a lot of satellites under this altitude. ISS is in the vicinity. It's a little lower, right? It's lower than 500 kilometers. But that's there's only a few satellites at lower altitudes. The ISS is boosted, right? So that's why it's still there. We're not going to boost ICON. This is its shot. So we're going to go for 575, and we'll stay there for more than a decade. Above that, DMSP satellites, NOAA satellites, those are usually in a polar orbit. Our orbits, we're flying out of Kennedy because we can, and we want this orbit. It's a 27-degree inclination. It's sort of a science orbit. Most many other satellites are in polar orbits, sun-synchronous orbits that are at 90 degrees or a little more than 90-degree inclination. Those are usually about 800 kilometers, 800 to 900 kilometers. So, and then geosynchronous is obviously much farther. The GPS satellites that are interfered with, you know, the density of the ionosphere can cause errors in GPS. Those are in tens of thousands of kilometer orbits and circular orbits, and so I think that's MEO, and then geosynchronous. So,
and what about the relevant zones in the ionosphere? Certain levels, how does that compare?
so we're in the top side ionosphere. So the main peak of the ionosphere is the F layer. It's usually about 300 to 400 kilometers or 200, 300 miles. It depends on your latitude. So the equatorial ionosphere is boosted and pumped up by what we know the equatorial winds that drive a dynamo at low latitudes. There's a natural wind dynamo that drives electric fields that pushes plasma and lifts it up at higher altitudes, but still below us. So we're still in the top side of it. So it's a nice smooth function of altitude with a peak around 300 kilometers, a little higher, and we're in the top of it. So we're still connected to that. Then below that's the E region. The E region's another local peak in the ionosphere that's driven by, the F peak is that red layer you see, and that's atomic oxygen. As you get lower, you end up with molecular ions, and those molecules are absorbing a different part of the solar spectrum, and you get another peak. And that's where you have this strong interaction. And that's where you wish you could spend your time, but we have to look at it remotely. So the E region is around 120 to 180 kilometers, or above, above, just below 100 miles. And that's a good spot for us. That's the other region of the ionosphere that's really important to ICON.
And geosynchronous is much higher, and they really worry about the radiation belts. So they're in the outer belt of the Van Allen radiation belts, which also respond to space weather, and so often can become extremely active, lots and lots of high energy particles, and the entire radiation belts can grow and engulf spacecraft that don't really want to be in the radiation belts. And so they worry more about that.
What's the altitude of that?
6.6 Earth radii is the easiest one for the geosynchronous spacecraft. I can think about it in miles.
Think about
Yes.
Thank you.
Great. We will go to the phones. We have Chris Gephardt with NASA Spaceflight.
Yes, can you hear me?
Yes.
Okay. Thank you for taking my questions. I've got two. For this particular mission, why an equatorial orbit instead of a polar orbit? What does this orbit advantage give you over a polar one? And for Northrop Grumman, can you go over and sort of outline, since the last launch attempt a year ago, what have you guys been doing with Pegasus, and what were the fixes or the root cause of that issue that you identified and fixed for tomorrow's attempt? Thank you.
So I think Tom's going to answer the why equatorial, and we're going to hold your question on the Pegasus because you're going to have a whole briefing on that launch system. So if we can hold that one to the next panel when the real experts are up here.
Well, there's a graphic for this somewhere else, not here, but it shows how from an equatorial orbit and the way we make our wind measurements, when we are crossing the equator, our wind instrument is making measurements to the north of the satellite. And we end up on that same field line that you're connected to when you're at the magnetic equator. You follow that dipole field line down, you can follow it down to where the wind measurement is made. And that's not achievable with a polar orbit. You have to be in a near equatorial orbit. There's a trade-off as well that the low latitudes are also where some of the largest, let's say, there are tides in the upper atmosphere, which originate in the lower atmosphere. These and they're not gravitational tides. They're not a lunar tide or a solar tide. They're just a motion. They're a motion of the atmosphere that's supported by on the planetary scale. Those are largest at the low latitudes. So we're focused in the low latitudes for a couple of reasons.
That's where all the action is happening. That's why we want to go there.
That's why whereas ICON goes where the action is.
ICON goes where the action is.
We have another question from the phones. It's Megan Bartell with Space.com. I think.
She's on mute.
We can't hear. I'm going to try one more time, Megan. We will move on. Any last questions from the room before we change it up? We will be going on to our second panel then. We are going to move. In the meantime, we have a video for you showing the launch sequence and deploy. We are back with our new panel. We have now Omar Baez, who is the NASA Launch Director, and Phil Joyce, who is with Northrop Grumman. He is the Vice President of Space Launch Programs. And we are now going to hear a little bit more about what brings us all the way to launch tomorrow. Omar.
Well, thank you. First off, I want to thank the media for being here. This is how we get our message out primarily to our taxpayers who are funding this. So thank you for being here and being that conduit for them. And I do want to thank our team that I have the great privilege of leading, starting with Launch Services Program here at Kennedy Space Center, our partners, Northrop Grumman, our customers' headquarters, NASA headquarters, and NASA Goddard Space Flight Center, and our ultimate customer, which is Thomas, who you heard before at UCB Berkeley. And I want to apologize for delaying you guys for the last 11 months, but we wanted to get things right on this rocket. There was no, we have no second chances on these type of missions, and we want to get it right. In the months that have preceded this, we've done a number of tests, both on the ground, and we've taken the rocket up with the L-1011 several times to try and lick this thing. We're only able to see it in flight, and flight's a very difficult thing to model on the ground because you have several components going on at once. You not only have the altitude, you have the vibration, you have the air buffeting you, the airplane's making its own vibrations with its turbines going. The atmosphere is a little bit less as we go up, and funny things happen when you're at altitude, and the temperatures get colder, and it's we had a system that we had a new component go in there, and quite possibly we may have seen this gremlin show up before, but we didn't have a visual cue into it. Now we did, and we had to do something about it. And that's what's taken us this long to come to grips with what those things were that were making our rudder position indicator get active, something that we don't want to see in flight, and something that we haven't experienced since we put several fixes in. So I hope that kind of explains what we've been doing. We did put the spacecraft aside while we did these tests so that we didn't put it in harm's way. And if we could roll a video that I have. This is the Icon spacecraft. And this is the solar array deploy and CPT that they spoke of earlier. This was done in August into September to make sure that during the hiatus that the spacecraft was off in a corner being kept in conditions that something didn't go wrong. This is a shot of the spacecraft being mated to the Pegasus. This happened on September 9th. On September 25th, we brought it out to the first reusable zero stage, that L1011 Stargazer that you see there. And this is the flight crew bringing it into the on its ferry flight here on October 1st to the skid strip at the Cape Canaveral Air Force Station, which I want to thank the folks at the 45th Squadron here and the folks at the 30th for supporting us all the way through this. And so I said a lot, and we saw this video. The important thing is tomorrow. The team will get working on the rocket about 2 in the afternoon. We'll have our management on station about 5 in the afternoon. They'll be powering up the Pegasus, the L1011, and hopefully, if all goes well, we'll lift off from the skid strip about 8:32 in the evening, and 58 minutes later, we'll be in the drop box, and we'll be able to drop Icon and the Pegasus and light it up and set it on its way. We do have a 90-minute window, so if the first attempt is aborted or we're late doing something on the ground or the weather gets us, we do have a short buffer there of about an hour, hour and 15, where we can adjust and still make it so that Icon can launch tomorrow. And with that, I'll turn it over to Phil Joyce.
Well, thanks, Omar. I want to second a lot of the things that you said about all the people that have been involved to get us to this point. You know, it's really says something about a team when you have a lot of adversity, and Icon is certainly no different. This is an incredibly complex machine. We saw some things on our previous launch attempt that none of us were comfortable with, and we decided to stand down and go address those and make sure that we really understood exactly what was happening there. That required, as Omar said, a really extensive ground test, modeling, simulation, and flight test activity to get to the bottom of what was really an extremely challenging problem, one of the most challenging that I've seen in my career in this business over some 30 years. But we got there. We with NASA, were able to get to some surprising results that told us a little bit more about the system that we have on the Pegasus, and educated us to the point where we could make some really smart corrective actions. So we implemented those. We got all the stakeholders on board, and I want to thank the science team and the headquarters team and all at Goddard and at Berkeley for sticking with us and actually being part of the solution here. And I think it says something about the strength of our relationship and the teamwork that we've enjoyed at Northrop Grumman over the last 3 decades on Pegasus with NASA. It's been a very special relationship. It's one we will continue with NASA. But all the things that we did in terms of qualifying and the flight tests that we performed with the system in its modified state give us great confidence that we're ready to go. And there's nothing better than a launch day, and we're all fired up and ready to go at Northrop. Looking forward to giving Icon a great ride.
Fantastic. We will go to questions in the room, and then we'll take them from the phone as well. Sir.
Jim Siegel with Spaceflight Insider. I understand that this is the 44th mission for Pegasus. Can you tell me if there are any future missions on the books, and when will the next Pegasus mission be?
Well, we don't have any current contracts, but I'm happy to report that we have two Pegasus vehicles out of Vandenberg that are in a pretty advanced state of integration that are available. We're talking to several potential customers for those. Our L1011 aircraft is as healthy as ever. The team at Mojave that maintains that airplane keeps it in tip-top shape, as illustrated by getting out here without any major observations or problems on the aircraft. So that aircraft's going to be supported for the foreseeable future, and we're looking to continuing Pegasus for as long as there are customers.
Steve Clark, I think you were.
Hi, Stephen Clark from Spaceflight Now. could one or both of you sort of talk in a little more detail about what exactly you were seeing on the launch attempt last year with the rudder movement, and what the investigation showed was the cause, and what corrective actions you implemented to resolve it? Just some more detail. I'm not sure I ever really fully grasped what you were seeing.
Yeah, so the Pegasus Stage 1 flight is an airplane, right? So there are 3 control surfaces on Stage 1, two elevons and a rudder. And it was the rudder actuator that we were seeing some anomalous position feedback readings, basically noise spikes in the feedback line. We didn't understand those, but they were significant enough that we were concerned if we launched with that condition present, that those noise spikes could couple into our control system and cause a bad day. So we elected to stand down at that point and do an investigation. We pulled that hardware off the rocket. We got it into our labs in Chandler, Arizona at Northrop Grumman, and basically replicated as best we could on the ground. And Omar pointed out how difficult this is to do on the ground, the environment that system was seeing while it was being carried around at 40,000 feet and minus 40 F on the L-1011. We were able to do that and set those tests up and able to recreate the problem, and that enabled us to get to the cause of it and identify several parts of the system that made us a little bit more vulnerable to that kind of a noise. And so as any kind of a complex problem like this, and this is why the investigation took a long time, usually has several causal factors, and this one was no different. There were actually 5 or 6 different things that we thought were coupling into this phenomena that we were seeing, and what we did to correct the problem is we went and attacked all of those. And so we modified our electronics to be less sensitive to this. We modified some of the hardware in that feedback circuit to be more robust to the environment that the L-1011 provides, which is a very unique and challenging environment. And then we went back and demonstrated that the modified systems would handle those environments in the lab. And then we conducted 2 test flights out at Vandenberg, one that simulated a sort of a ferry flight, the one we just did last week, the other that simulated a launch attempt where the L-1011 is configured a little bit differently, and we could see a little bit different environments, and verified in both of those conditions that we didn't see any of those spikes return. And then the final test, and all of us were on pins and needles for 5.5 hours while the aircraft transferred from Vandenberg over to the Cape. We were monitoring that circuit the entire flight, and we're very happy to report that it was as clean as anything we've seen. So that gives us great confidence going forward into tomorrow's attempt that we've got this problem behind us. But just in case, we've instituted some new mission rules to look for these kinds of things, and with NASA, we'll evaluate anything we see during the launch attempt and make a call that is completely based on mission success, because that's what we're all about here, is getting this satellite to orbit.
Great. Oh, follow-up?
Just a quick follow-up for Phil. You mentioned the new hardware on this mission. Are those the fin batteries that are flying for the first time? And was there any relationship between that and the signatures we're seeing?
The fin batteries are actually not new. They're the legacy thermal batteries that we've been flying on Pegasus for years, many years. The actuator control unit, the electronics that control the servo on the actuators themselves, that is new, and that is one of the components that we did some slight modifications to correct for this issue.
Marcia.
Marcia Dunn, Associated Press. Where will the drop actually occur? Where will the plane be? At what altitude, and how many people on board for the deploy?
So, Marcia, we're going to be about 100 miles, 50 to 100 miles off of Daytona Beach when the drop occurs. We do have a 40-mile long box to be able to launch it in, but you're going to get a special treat, and you're going to hear all about the flight crew and the airplane in the next panel.
And what's the altitude for the drop?
39,000 feet.
39,000, thanks. Okay.
Great. We do have a question from the phones. There's a question from Chris Gephardt, NASA Space Flight.
Yes. In terms of that Dropbox location, you can launch anywhere within that, if I'm understanding it correctly, right? So if there's a thunderstorm at the preferred drop location, you can reconfigure and get to another part in that box away from weather if needed. Is that correct?
In theory, yeah, that we could steer around it, but the last thing we want to do is fly a airplane with a rocket under it anywhere near a thunderhead. So yeah, if the conditions are right and we're able to get either away from the thunderhead or high above it, we might be able to do something. But in reality, most thunderheads are anywhere from 10,000 feet to 50,000 feet or more. So it would be very unlikely, but we can certainly steer around some of them. And we can delay the flight or loiter for a little bit and do another run in case time is helping us and having that thunderhead or whatever it is we're trying to avoid move off.
Any more questions from the room before we move on? Yes, sir.
Jim Siegel from Spaceflight Insider. Question for Phil. So the Pegasus concept, dropping a rocket from an airplane, is very unique. Is anybody else anywhere else in the world doing that, or is this unique to Northrop Grumman?
Well, you may have heard of our friends at Virgin Orbit. So their concept looks very similar to Pegasus. There's no wing on their rocket, and they launch it from a 747. But we're really proud, and it's part of the Northrop Grumman and prior to Northrop Orbital Sciences legacy. The Pegasus was the first privately developed space launch vehicle and the first air-launched space launch vehicle with the first flight in 1990. And as noted, this is mission 44. And it's been a very robust system, capable of 1,000 pounds to low Earth orbit, can launch from anywhere in the world, and it's one of our crown jewels.
Thank you. We're going to move on to our third panel. And as an intermission, we're going to show you a movie on the Cygnus launch. This was NASA's last Pegasus launch from December of 2016.
LC, PLT, copy.
LC Peg, Peg is go for launch.
PLT, LC is go for launch. PLT confirm.
LC, PLT, PLT confirms go for launch.
Drop on my mark. 3, 2,
1. Go for release.
Pegasus is away.
And drop. Pegasus is away.
LC, PLT.
Ignition of the Pegasus rocket with Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
Hello, we are back. We now have with us Bill Ulrich from the 45th Space Wing. He's a weather officer. We also have Don Walters, who is the chief pilot of that Northrop Grumman Stargazer L-1011 that we were just hearing about. And we're going to hear a little bit more about what we can expect tomorrow night. So for starters, Bill, tell me, Will, I'm sorry. Apologies. Tell me a little bit about why the 45th Space Wing and weather's important here. What are you bringing to the
the 45th launch? Space Wing and the 45th Weather Squadron, our primary mission is to ensure safe access to space, and of which the 45th Weather Squadron, of course, is the weather component. So to ensure that our launch customers in the Eastern Range are launching into safe weather conditions, we use a variety of weather tools to ensure that they are doing so, including weather radar, high-resolution satellite imagery, lightning detection equipment, as well as weather balloons. And we use all of that equipment to evaluate a total of 10 lightning launch commit criteria, or 10 rules, basically, that we need to ensure that the customer is not launching into adverse weather conditions. And those 10 rules are really meant to steer the vehicle clear of any potential thunderstorms that are ongoing or could potentially develop, or those clouds that could potentially trigger lightning with the presence of a rocket in the vicinity. So this particular mission is a little bit challenging in the sense that we're talking about the drop box being about 50 to 100 miles offshore. So it's not really in the presence of some of these ground sensors that we typically use when we launch from anything here at Cape Canaveral. We're talking about something that's 50 to 100 miles offshore, but we can still supplement that information with our radar here at Patrick Air Force Base, as well as high-resolution satellite imagery. So ultimately, at the end of the day, we'll still be able to evaluate most of those Lightning launch commit criteria to ensure that they launch safely. It also helps that they're also going to be launching from 39,000 feet in the atmosphere above most of the weather that we experience here on the ground.
And so what's the answer? What's the weather going to be like?
Oh, geez. I knew you guys were going to ask me that question. Unfortunately, here I am on the stage again being the bearer of bad news. I feel like I have been for the past couple of launches, but the good news is the launches have eventually gotten off the ground, and eventually this one will as well. But for tomorrow, if we take a look at satellite imagery right now, we've got a couple systems that are going to kind of interfere with tomorrow's launch. And you can see all that organized cloudiness off the east coast of Florida, stretching up the eastern seaboard. It's all associated with a large area, a surface trough, basically, which is an immature area of low pressure that is triggering those showers and thunderstorms up and down the east coast. What you can't really see shrouded underneath all of those clouds up and down the eastern seaboard is a cold front. And that cold front is expected to move a little bit closer to us during the day tomorrow, and then it's expected to shift a little bit further to the south on Thursday. So if we look at tomorrow's forecast, with the presence of that surface trough and that cold front to our north, conditions will be quite unstable tomorrow, kind of like they are today, kind of like they were last night, such that we expect scattered showers and isolated thunderstorms in the area, even tomorrow evening. Now, the winds and the temperature that you see there is what the conditions are expected to be for takeoff, which is, light winds out of the northeast, 7 to 9 miles per hour, and temperatures in the low 80s. But there will be, unfortunately, scattered showers in the vicinity of the area, but also, and especially, there'll be even more activity out over the Atlantic water. So our primary concerns are the cumulus cloud rule and the lightning rule. And with that, unfortunately, we do have a probability of violation of 70%. But if we go to the backup day, hopefully we don't need to have a 24-hour delay, but should we, conditions are going to be a little bit better. For takeoff, we're going to have a slightly stronger winds, unfortunately, which can be a crosswind can be an issue for takeoff. The winds will be out of the northeast around 15 miles per hour. But overall, the coverage of showers is expected to be lower as we see that cold front, or what's left of the cold front, I should say. It's still kind of early for us to have a cold front here in central Florida. What's left of it will start to bring in some drier air from the north. So overall, our primary concern is the cumulus cloud rule with a 40% chance of POB. So I wish I had some better news, but ultimately we're going to do our best with all the tools that we have at our disposal to ensure that tomorrow's launch or potentially Thursday night's launch is as safe as possible. Thanks.
Thank you very much. Let us go to Don. Tell us a little bit about piloting, hopefully with good weather, what that experience is like when you take off.
Well, thank you for the weather briefing. We rely on a large group of people to give us information to ensure that the safety of the flight, that's our primary concern, is the safety of the flight. On the ground, our main concerns are precipitation, winds, and lightning. Once we're in the air, one of the advantages of the L-1011 system is that it's a very mobile, very fluid system, and tactically we can move around some of the storms that we're talking about. Once we're in the drop box, of course we have to have a clear shot for the rocket, but the crew has some flexibility to help deviate around some of the storms locally. But on the ground for takeoff, it's just water, wind, and lightning.
So I think we have a video of the path that you expect to take. Can you talk us a little bit through the entire process of dropping off?
Absolutely. So we've planned a 58-minute flight. The goal is for us to be at the launch box at a specific time, at a specific speed, at a specific altitude. So we'll be taking off out of the skid strip, flying a pattern away from the launch box to gain altitude. As soon as we gain altitude, we're going to turn back towards our launch point and take weather observations over the launch box so that we know the wind, the temperature, the turbulence, and the cloud conditions. Then we'll fly out around, turn around, give us time to configure the systems for launch. When we hit the launch box or hit the launch point, we'll drop the rocket, turn slightly out of the way, and watch the rocket fly off into the west.
So I have a question for you, because you've talked to me about this before. What it feels like when you're in that plane and you drop the Pegasus.
So it is the most exciting part of the flight. You can imagine we take a 52,000, the plane is flying in a stable condition. When you drop 52,000 pounds all at once, the lift that was on the airplane still exists, and as the rocket falls, we lose that gravity. We lose the 52,000 pounds, so the plane climbs fairly rapidly, about 1,500 feet as the rocket is falling. Not only is that an exciting part of the flight, but it also gives us separation for safety from the rocket as we drop it.
All right, well, we are hoping for smooth skies tomorrow, and we will go to questions in the room. Marcia.
Yes, Marcia Dunn, Associated Press. How many people on board for the launch, and how many seconds after the rocket drops does it ignite, and who's actually somebody pushing a button, or is it all automated at that point following the drop? How does that?
So the number of people on board, our minimum crew for a launch is 5. We have 3 pilots and 2 launch panel operators. Occasionally, we do bring additional pilots or launch panel operators along for training. I've killed launch. The rocket drops for 5 seconds before ignition takes place, as long as all of the safety parameters in the rocket are go for ignition. And what was the last question part?
Does someone on board provide?
So the unique part of Pegasus is that when we fly into the launch box, the crew is just sort of the instrument for a huge team that's on the ground monitoring all the safety parameters. So as soon as we are in the launch box, we wait for a command from our launch conductor to drop the rocket, and it is actually, he's sitting right behind you, my co-pilot, Steve Gunn, is the one who actually flips up the switch and physically drops the rocket.
And the ignition, is that also done from the crew
No,
on
no.
board?
Once the rocket is clear of the airplane, it's completely autonomous.
Autonomous, okay. Thank you.
Steve Clark.
Hi, 2 questions for Don. Since you've done this before, can you describe the sort of the physical sensation of that feeling on the airplane when it wants to climb so quickly once you let go of that 52,000 pound rocket? And I have one follow-up.
Sure. Well, the best way I can describe it is if you've ever ridden in a ride that pushes you down in your seat rather quickly. So as we lose the weight, the airplane rises at a fairly rapid rate, and you can feel, there's 2 things that you feel. One is that you can feel yourself being pushed up against the seat. The second thing that happens is when airplanes fly, we balance them. We have a term called weight and balance. And so when we drop the rocket, it changes the balance of the aircraft rather dramatically, which creates this pitch-up moment. So what winds up happening is we let the airplane climb to not resist that too much, exceed a structural limit. And as it starts climbing and dissipating energy, then we can push over and kind of level the plane off again.
And just to confirm the numbers, what's the target altitude, airspeed, and azimuth for the release, if you have that?
The target altitude is 39,000 feet. Our target airspeed for launch is about 0.82 Mach, and our launch heading is about 113 degrees magnetic.
All right.
Jim Siegel from Spaceflight Insider. 2 questions. First of all, is there a certain meeting that takes place tomorrow at a certain time at which it was going to be decided whether the weather is going to be favorable or not, or is it kind of all the way up till launch time, or time where you take off around, what, 8:30 or something like that? And then the second question is, what happens if both Wednesday and Thursday are not acceptable from a weather performance? Then what happens? Is there a backup date after that, or what?
And we're wrapping up, so answer quickly.
Okay, so yes, there will be a meeting tomorrow. Our senior management meets with NASA to decide what the risk factors are and what the probability of success is. And I believe we have Thursday and Friday as backup days.
Fantastic. Thank you all so much today. We had one quick question we weren't able to answer, and I want to make sure that Nikki is available to answer that question now, which was the cost that was asked earlier.
Okay, so the cost, the NASA cost for ICON is $252 million, and we're happy that we have not violated that cost at all. And for those of you who don't do Earth radii, geostationary is 22,000 miles up from the above the sea surface.
Fantastic. Please tune in for the the launch coverage, which will be tomorrow night, nasa.gov/live. And for more questions about ICON, nasa.gov/ICON. We've had great fun today. Looking forward to tomorrow. Bye.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Please stand by for a voice check from NPR.
Station, this is NPR. How do you hear me?
We have you loud and clear, NPR. How do you hear us?
You sound great. Hi, this is Manny Sophia. Thank you so much for taking time to talk to us from space. Very cool. I'll get right to it. Apparently, y'all are busy up there. So, Jessica, I know you two are friends and that you've been training together for years. What's it like to finally be up there in space together?
It's really difficult to describe. Christina and I were both in the same class. As you mentioned, we started together in 2013, so it's been 6 years now. And in particular, the last couple of years, Christina and I spent a lot of time training together in Star City, the cosmonaut training center about an hour outside Moscow for the Russian Space Agency, since we both flew up here on Russian rockets. And we were essentially, we called ourselves Space Sisters because we were together, really joined at the hip, going through all the classes together. It is an amazing experience, of course, just to even be up here and have the dream of being in space come true, but to come through the hatch and see my best friends, my classmates, my astro brothers and sisters makes it even more special than it already is. So we are all smiles up here with this reunion.
That's great. Okay, Christina, this is a question for you. There's been some press about how you're slated to set this record for the longest single space flight by a woman. I'm genuinely curious, does it ever bother you that your accomplishments are often talked about in terms of your gender, or do you think it's really important to mark these milestones?
That is something I've done a lot of thinking and reflecting on. And in the end, I do think it's important. And I think it's important because of the historical nature of what we're doing. And that in the past, women haven't always been at the table. And it's wonderful to be contributing to the human spaceflight program at a time when all contributions are being accepted, when everyone has a role. And that can lead in turn to an increased chance for success. There are a lot of people that derive motivation from inspiring stories from people that look like them, and I think it's an important aspect of the story to tell.
What about you, Jessica? How do you feel about it?
I think Christina gave the perfect answer. You know, it is really what we're doing now shows all of the work that went in for the decades prior, all of the women that worked to get us where we are today. And I think the nice thing is for us, we don't even really think about it on a daily basis. It's just normal. We're part of the team. We're doing this work as an efficient team working together with everybody else. So it's really nice to see how far that we've come.
Yeah, absolutely. That makes sense to me. In recent years, there's definitely been more and more opportunities for women in space, and there's been a lot of progress. What do you think still needs to be done to change the field so that it's truly equitable?
I think anytime you're involved in an industry that has such a long lead time for technology advancements to be integrated into that industry, there are some legacy things that go on. I think that we had that highlighted last year. We have a situation where we had a spacesuit cause a change in personnel to a spacewalk. And so I think just allowing the time to pass, that the different things that we have come to recognize are required to incorporate people of all shapes and sizes fully into the program. But I don't see any institutional things that change. Jessica and I are held to the exact same training standards. We're treated the same in terms of assignments for various missions on board, and I think that's the important part. We work together as a team, and between us and between the crew and our teams on the ground, we don't look at gender and we don't see it as a barrier.
Yeah, I'd like to touch back on the spacesuit situation. I mean, for years, there's been some concern about the availability of those spacesuits that fit women. And of course, like you said, that was kind of brought back up after the canceled all-women spacewalk. So are you both fully satisfied with the spacesuit situation up there? Like, are we good?
Yes, that spacewalk that had originally been planned to be conducted by Anne McLean and myself was not canceled itself. It still happened with a different crew to make sure that we matched the spacesuit sizes and conducted that spacewalk as safely as possible to get the mission done. We currently do happen to have 2 medium spacesuits on board now. That was a job that I was able to do in the meantime to configure a new one. So I think Jessica and I both have trained throughout our 6 years together in the sizes that are available on board right now.
Christina, I'm interested on just like a personal level. Was that disappointing for you, or were you like, this is all about the job? I mean, I know there was a ton of press around it, so I'm just interested in like a personal level, what that felt like.
Absolutely. I am fortunate to be up here with crewmates that I have trained with because we're all in the same astronaut class for many years. I consider it a privilege to go out the door and conduct a spacewalk with anyone on board, and so it was absolutely not a disappointment. I think that the correct decision was made to accomplish the mission, to do so as safely and with the most risk mitigation in place as possible. So I think it was a great move, and Anne and I, of course, were up here together, and the decision was made on board. So I would never call the opportunity to contribute to the program by conducting a spacewalk a disappointment in any way at all.
Yeah, can you give me a little more information on the decision-making that was behind the spacewalk and whether or not to cancel it or go forward with one female astronaut and one male?
Interestingly, as Anne and I were able to explain and talk about after the spacewalk, Anne made that decision, and the teams completely supported her in that decision. It was discussed on board, and it was discussed with the teams on the ground, and we're just so glad that we have such a supportive team that all knew that that was the right call to make. And that decision was made, and that call was made after gathering the information on the first spacewalk that was conducted in a series of 3. So it's just wonderful to be working with teams that all see the same priorities and that all know that our main mission here is to do our job safely.
Okay, Christina, you just said you've got 2 medium spacesuits ready to go. Is there a chance that we are going to see Jessica Meyer, Christina Cook, all-woman spacewalk going on?
Yeah, so right now we have 5 EVAs coming up, 5 spacewalks coming up to replace the batteries. So basically to upgrade to the new lithium-ion batteries that will better serve the power supply aboard the space station. Since we have a series of 5 spacewalks coming up, and we're doing that in a short proximity of time, as Christina mentioned, everybody up here is fully qualified to do a spacewalk. So I think that we can see any possible combination of personnel going out the door. We'll all be doing spacewalks, and there'll probably be several different combinations. We still don't know the final assignments for all of those, but yeah, there's a chance that we could be doing it together. Just any of the combinations are a possibility.
Awesome. I am going to take that as a hopefully on my end. Okay, this is a genuinely just curious space question that I couldn't not ask, and it's for both of you. You dream about this and you picture these moments of being in space for years, I imagine. What's the one thing that was the most different from your expectations? The thing that surprised you the most about being in space?
Well, since I just got up here, I think some of the things that have surprised me so far, it's very interesting because, of course, we spend so much time training on the ground. And in Houston, we have a full mock-up, life-size, of all of this. And we also have the Russian segment. We don't have as high fidelity in Houston, but in Star City, we also have a good mock-up of that. So we get there's this level of familiarity when you arrive on board the space station. Okay, I've trained this, but then it feels really, really different. And I think the biggest difference is because we are just using the whole three-dimensional space in microgravity. When I have been training in Houston in the lab, for example, where we are right now, you're always standing on the deck like we are right now, and you're always working in that orientation. But up here, right now we're on the deck, but then 1 minute I might go over here and be completely in the other orientation like Christina's showing you now. And what I found so far, it's really interesting when you're thinking about the plasticity of the human brain. For me right now, being a newcomer on board, once I know where I'm going and I get into that position, but once I've spent several minutes or a while in that position working, my brain kind of reorients to, okay, feet must be down, I must be on the deck again, but I'm really not. I might be up here. And so after I come out of that position, it takes my brain a minute to figure out my spatial awareness and figure out where I'm going. And from talking to Christina and our other crewmates up here, they've mentioned that, they had the same kind of thing at first, but then at some point your brain sort of shifts. And instead of using that map that you've been trained to in the gravity environment your whole life, instead your brain is kind of picking up on cues using, for example, pieces of equipment, and you know where it is. So even if I'm up there and I come out, I see this piece of equipment, which is the cycle ergometer, so the bicycle that we have to exercise on the space station. And my brain knows where that should be in relation to everyone else, to everything else. And so then I can just continue on and I know where I am. So I'm kind of waiting for that shift because right now it's really interesting. Every once in a while, the space station kind of flips on me and I don't even notice it. But I think it's going to be really interesting for me as a physiologist to observe that kind of plasticity, how the brain can adapt and change to new environments.
Okay, well, Christina and Jessica, thank you so much for your time. Congratulations up there.
Thank you so much.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all the participants from NASA headquarters and NPR. Station, we are now resuming operational audio communications.
Hi, I'm Lindsay Aitchison. I work on spacesuits. This is Ask NASA, and I'm here to answer your questions. How will NASA get to the moon? Well, we have a brand new SLS, Space Launch System rocket. It's launch day, and all the fire and smoke, all the power, you're up in space, and at that point, you can lose your abort system, so let that go back to Earth. And then one more big push, and now your Orion is taking 3 days to fly all the way over to the gateway where it parks, and now you're ready to start the next phase. This is where you're going to start to unload the science equipment and pull out your spacesuits. And then it's time for the fun stuff. We're going down to the lunar surface. So once you put on your spacesuit, you're going to crawl into the ascent module, and that'll take you all the way down to the lunar surface. Once you're there, go outside and start doing science, geology. You spend a couple of days. Once you're done doing all that, you climb back into your ascent module, take off, and return to the gateway. Once you get back to the gateway, you're going to unpack all of your science and everything you want to take home, put it into the Orion. Everybody truckles back into the Orion, and you start that 3-day journey back home. Why do we need the gateway to get to the moon? We're going to the gateway because it makes a lot of sense for sustainability. That means you can go back multiple times and use it to get anywhere around the moon. You can also use it as a staging point on our way to Mars. How will humans explore Mars? Well, that's actually kind of what we're trying to learn by going back to the moon. In addition to learning so much about how the moon was created, which tells us how Earth was created, we're really practicing all those new technologies and those new ways of living off the Earth before we go to Mars. So once we get there, we'll have practiced everything on the moon, and then we can head out.
So what will the gateway Wi-Fi password be?
Hopefully something easy to remember.
Would you go to the moon?
Absolutely. Do I get to choose who goes with me?
Have you worn an astronaut glove?
Oh, hey. Yes, I have. As part of a spacesuit engineer, we try on all of our own hardware.
How does NASA throw a party?
You plan it.
If you could go anywhere in the solar system, where would you go?
Probably Mars. I mean, it's far enough to be interesting, first one there, but still close enough to home if you have a problem.
What's the coolest thing about a spacesuit?
Coolest thing about a spacesuit is that they're made to fit you exactly so that you can have all the mobility you need to both do your job and stay alive.
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Leading the way to study where Earth weather and space weather come together. NASA is on a mission that will determine the future of how we communicate every day on Earth.
Broadcasting live from NASA's Kennedy Space Center, you're watching launch coverage of the ICON satellite. Its mission? To study the meteorological frontier where Earth meets space. On your screen is the Pegasus XL rocket, which contains ICON. Approximately 15 minutes from now, this rocket will launch NASA's latest Earth science mission off the eastern coast of Florida into a very unique and unexplored area of space. Hello everyone, I'm Jennifer Wolfinger, and thanks for joining us for this highly anticipated launch. The Ionospheric Connection Explorer, or ICON for short, will help scientists understand the physics of our space environment, as well as protect our communication satellites and astronauts while they're in orbit. The ICON mission is managed by NASA's Launch Services program based here at Kennedy Space Center. What separates ICON from traditional rocket launches is that the Northrop Grumman Pegasus XL rocket will launch from the bottom of a Stargazer L-1011 airplane instead of a stationary launch pad. The Stargazer took off from Cape Canaveral Air Force Station about 45 minutes ago. You can see it there on your screen, with the Pegasus attached to its belly. This aircraft, the world's only operational air launching system, is a mobile launch platform that can be deployed from anywhere in the world. The plane will release the rocket 50 miles off the coast of Florida at approximately 9:30 this evening. This is the first of today's 2 possible drop attempts. What you're seeing now is a bird's eye view of Stargazer's flight path. The path follows a long oval loop, also known as the racetrack. When the plane reaches a certain point on the path, the Stargazer will drop the Pegasus rocket. If the first attempt is a no-go, Stargazer will loop back to the sweet spot and make a second drop attempt by 10:55 p.m., which is when the launch window closes. Now here are a few more quick facts about the mission. Once ICON is launched and reaches 40,000 feet, it will be released in free fall for 5 seconds before its first stage rocket motor ignites. The launch sequence from drop to payload separation will take about 11.5 minutes. The Pegasus XL is over 57 feet long and weighs nearly 53,000 pounds. Icon weighs nearly 650 pounds, about as much as a vending machine. When in orbit, the satellite will travel at more than 4 miles per second. That's almost 30 times faster than a commercial airliner. Icon will study changes in the ionosphere where Earth's weather meets space weather. The satellite solar array is over 8 feet long and 2 feet wide, a little bigger than a common door. Icon will study the ionosphere for 2 years to provide a better understanding of this complex region of space. We are approximately 12 minutes from launch, so let's head over to the Mission Directors Center where NASA's Joshua Santora and Malcolm Boston will give us a deeper look at this unique launch. Welcome, guys.
Hey, thanks, Jennifer. Good evening to you and good evening to everyone out there watching us. We're coming live to you from Hangar AE at the Cape Canaveral Air Force Station on the east coast of Florida. And tonight, it's Pegasus Launch Control.
That's right, Josh. Malcolm Boston here with NASA's Launch Services Program, ready to launch.
Can you give us a little update on kind of how the countdown has gone tonight?
Very smoothly. We worked a couple of adjustments, but no real issues, and we're ready to go.
Want to be clear, what you're seeing actually there, that's the nose of the Pegasus. So that's a camera mounted to the bottom of the L1011. So you're seeing the front edge of that. Obviously, it's nighttime here on the East Coast, so that's what's going on. The big story yesterday was the weather. Today, it is not nearly as big of a story. So we have a few things we're keeping an eye on. Their precipitation has been one of the biggest ones. We can't be flying through rain. We have a 20% chance of violating those constraints. So we're keeping an eye on that, but we'll take a look at the radar. Yesterday, this radar was filled with lots and lots of dark greens and reds and yellows, and there it's very splotchy, which is what we want to see. On the right hand of your screen there in the middle, you can see that red rectangle, or part of that red rectangle. That's the box that we call it. The plane is headed for that box. This is a space out over the Atlantic Ocean, about 40,000 feet in altitude, 10 miles wide and 40 miles long, and the plane has to be inside that box in order to drop the Pegasus. We'll talk more about the process in just a few minutes, but once it's there, it has to be traveling. The plane needs to be traveling at the right direction, speed, and in that space, and then it can launch the Pegasus. Malcolm, can you tell us a little bit about the rocket tonight? Tell us about the Pegasus.
Pegasus is unique, the only operational rocket with that's air-dropped. She's about 57 feet long, a little bit more than that, approximately 52,000 pounds at drop. And this will be the 44th time she's been used to launch something in the Space Force.
Yeah, we also had up on screen a minute ago, we had an image that had waypoints listed. We call this the racetrack. If you kind of see this, it kind of looks like a racetrack pattern. This is where the plane is actually flying. This is the path that it's flying. You can see there's a circle moving towards the PIP section, and that's the actual, the small one to the left of that is what's moving. That's the airplane. We're actually going to take a look now at a video of this past year. So for the past 11 months, we heard from our pre-launch broadcast a couple days ago that there were some major issues, not major issues, but just issues. We attempted to launch almost 11 months ago. Malcolm, what are we seeing happen here over the course of the past 11 months?
Well, this is footage of Icon being pre-launch checked. At this moment, they're buttoning up to fit inside the payload fairing. But over the past 11 months, we've also had some other activity going on. One is troubleshooting and resolving the issue that scrubbed us out 11 months ago. And the second team has been working on just caretaking of the rocket itself and the spacecraft.
Yeah, we had to fly it out to California. That's the facility where they can actually take the thing apart and really do what needs to be done. So this is them actually repacking the Pegasus on the L1011 to fly it back out here to the East Coast. It arrived a couple weeks ago, so everybody is so anxious for this launch. Such a high level of confidence of everybody's done their homework, they've done their research, they've worked the challenges, they've all come to this place where they're comfortable and they're confident moving forward. We are actually tuning in. So I want to point out right now that our clock is a little bit off of what was anticipated. And part of that has to do with that we have a mobile launch platform. So we're a few seconds behind where we thought we would be. So currently our clock says we're looking at launch a little bit closer to 9:31. So we're kind of just feeling that out as we go. And that's largely dictated by the pilot's position. So ultimately, the clock is dictated by where he is, because he has to be inside that box. So in just a minute, we're going to be listening in. We're going to have a couple polls coming up. But Malcolm, really quickly, can you tell us about the teams that are involved, the 4 teams involved tonight?
Well, yeah, as you said, we have 4 teams. One is the air crew, 2 pilots, a flight engineer, and at least 2 launch panel operators. The second team is the Northrop Grumman engineering team monitoring Pegasus itself. And then we have the combined LSP spacecraft Icon teams that are monitoring the entire launch operation. And our last team is our range safety provided to us by our colleagues at the 45th Wing.
Yeah, the range ultimately responsible for public safety. Correct. So they're looking at things like making sure there aren't boats in the area where our plane is flying. In this case, we don't have as much of a land concern because we're not launching from the land, so it's mostly out over the water and in the air. We are going to go ahead and listen in now. We should have Omar Baez, NASA launch manager, polling his team.
This is DNLM on the NLMnet for a final launch readiness poll. NASA CE.
NASA CE is go.
SMA.
SMA is go.
SMD.
SMD is go.
NASA Mission Manager.
NASA Mission Manager is go.
LSP.
LSP is go.
Copy. Teams ready to proceed.
All right, so there you go. You had Omar, again, polling his team. So all go calls, that's what we want to hear. So he'll be reporting out to the launch conductor in just a minute. We're going to actually jump into a video of the last time we launched a Pegasus rocket. So this is the Cygnus mission. I think you said you actually got to work this mission. Can you tell us what we're seeing here?
So right now we're seeing captive carrier, the pilot's heading for the drop box. Very shortly we'll see the Pegasus release from Stargazer, free fall for approximately 5 seconds, and then ignite the first stage engine. Pegasus is a 3-solid rocket motor, 3-stage vehicle. Each stage will burn for approximately 60 seconds.
So there you go, that drop. Again, tonight we won't get to see this in that way because it's dark outside. So we hope to have something for you to be able to see. But again, it's the nature of launching in the middle of the night. And that's okay. Again, we're headed towards that box, and like I mentioned, that clock is jumping around a little bit on us. That's okay. We're just rolling with the punches here. We're just under 6 minutes now, according to the official clock that we're looking at. And so coming up in just a minute, we'll hear Adam Lewis, the launch conductor for Northrop Grumman. He's going to be polling all of the teams to make sure everybody's in a good position. Again, our pilot headed for this box, this fictitious line drawn out over the Atlantic Ocean, 40,000 feet in the air, 10 miles wide, 40 miles long. And so as the pilot approaches there, he will be able to ultimately make that call. And we'll talk about kind of his role. He's got a pretty fun role, and in my opinion, it's a fun role for tonight. But let's go ahead. We're going to actually listen in now. Again, this will be Adam Lewis. You hear on screen. You see the current location, so you can see that red dashed rectangle there to the right. That's where we're traveling towards in PLCH for our launch waypoint. So again, let's listen in to Adam Lewis.
Copy L-5, check 174. At this time I want to poll for final launch countdown. Rock?
Rock, clear to launch.
Peg?
LC, Peg. The entire Pegasus engineering team and my son Jackson, who turned 10 years old today, are go.
NGLD?
NGLD is go.
NLM?
NLM and NASA are go.
We are go to proceed with final countdown at L-4.
All right, so good to hear that all 4 teams and Jackson are all ready to go. So we're excited for everybody to be on board tonight. We want to take a closer look behind the scenes here at this facility. There you see on your screen, this is Hangar AE. Some call it the telemetry center of the universe. Certainly for rocket launching in America, it is. Take a look at this.
The liftoff is the most exciting part of watching a rocket launch. But what you don't see is the dizzying amount of data sent between the rocket and engineers inside this renovated Air Force Base hangar.
The amount of data that comes through this building is astounding.
Chuck Duvall is Deputy Program Manager of NASA's Launch Services Program, which sends scientific and planetary missions into space. He says here at AE, launch managers can monitor every aspect of the rocket and spacecraft's health, so to speak. Hundreds of thousands of measurements, called telemetry, are displayed on computers in real time. But it hasn't always been so high-tech. 20 years ago, machines scribbled rocket telemetry on paper. Lots of paper.
This record would get to be this thick, and it'd be my job as a co-op student to go upstairs and roll that record out.
Hundreds of feet long.
Yep.
Today, rocket telemetry is far more visual and complex. There are close to 40 voice communication channels connecting launch teams from around the world, and they can view 16 or more high-definition camera views coming from the launch pad, several drones in the air, and even on board the rocket itself. And don't forget about the data. Telemetry is now stored on servers for future reference, and it's so voluminous, playing every launch going back to the early 90s would take close to 32 years. As the chief of telemetry and communications at Hangar AE, Reed DeVerde's group processes and distributes the data to the launch teams. And he says Hangar AE can now handle launching 5 different rockets at the same time, thanks to a multi-million-dollar upgrade.
All right, so a really neat look at the facility that we're being hosted in. I wanted to get back to the pilot tonight. Malcolm, can you talk about his role in this whole thing?
Well, the pilot's busy. He's not only transporting Pegasus and Icon to the drop box, but he's also responsible for Stargazer and his crew on board. And so he's going to be monitoring everything right down to the last second, right down to release, and actually making the final decision on when exactly to drop Pegasus. So he's a very busy man and monitoring a lot of data.
So we mentioned that our clock is moving a little bit based on the position of the plane, but also the pilot, if I understand correctly, he ultimately, like you say, he has to choose the right moment when he knows that things are safe for his crew. So again, even more reality of this clock is almost a suggestion for tonight. There's lots of things that are paced off of this, and we work to this, but lots of important things going on. We're going to keep an eye on this camera you've got on your screen. We should be seeing a fin sweep here any second. Just being able to see a little bit of motion, ensuring that everything's functioning correctly mechanically before this launch. I'm going to let you listen in now and enjoy the last few minutes.
Got negative comm. LPO, LC, voice check on Victor 2. And LPO, LC on 133.8.
So it appears that there's a communication challenge.
PLT. 264.8.
If I understand correctly, Malcolm, it sounds like we're having a challenge communicating with the plane. Is that correct?
That's what it sounds like, what they're working through the checklist, and we'll see a resolution here, hopefully, very shortly.
Count.net, the HIN 11 is in the box.
Copy in the box. PLT, LC for voice check. And launch team, we're going to abort, proceed to the abort checklist.
Okay, so we just heard an abort called, so I'm sure that the teams are going to take a minute and evaluate what's going on here. We're going to just stand by. We're going to try and gather some data really quickly before we speak too soon. I know that there is the potential that we could travel a racetrack pattern to kind of recycle and attempt a second drop tonight. I don't know if that's going to happen or not. We're going to, again, get back to you in just a minute.
Roger that.
Alpha 14 is not required, Elsie.
Coming back to you live from Hangar AE here at the Cape Canaveral Air Force Station. So we just checked in with the assistant launch manager for today, and we're getting word that we are going to racetrack.
Okay.
So they're still working towards confirming a time to launch. So again, there's a lot of things that have to happen in approximately 30 minutes. On a nominal racetrack, that's about how long it takes to get around and make it back to the box. So that's great news. So obviously it's nice to have that capacity to be able to cycle through and do this again. So obviously it sounded like there was a comm issue. They were having issues communicating with the plane. That's critically important. And so we actually, I think we're going to go ahead and pass it back over to Jennifer in the studio and get a little bit more information from her about the science of ICON and the instruments on board. Jennifer?
Thanks, Joshua. While we wait for a launch update, let's learn a little bit more about the dynamic zone of our atmosphere that ICON will be studying.
Longing for more space, open skies, and exotic travel? Then look up. About 30 to 600 miles straight up at the ionosphere, Earth's interface to space. Nestled far above the clouds but below outer space, this little understood destination invites you to explore its many features. Experience both the weather from Earth and the weather from space. Marvel at the ballet of radio waves and navigation signals, like GPS, leaping through this particle paradise. Sit back, relax, and take in the aurora, some satellites, and the International Space Station as they sail by. And you'll want your camera handy for one of the region's signature features, bright and colorful air glow. This daily show is made possible by the ionosphere's own swarming charged particles, because that's what the ionosphere is. It's all charged particles. During the day, enjoy the sea of particles, freshly energized by the sun. As the sun sets, this particle party relaxes and the air glow thins. Our quieter nightlife lets you gaze into clearer skies. The ionosphere is in constant motion, an amazing effect of space weather. Don't miss when solar storms rain down. The storm separates the particles even more, making this colorful region delightfully more dense in some places and stunningly sparse in others. And don't forget about storms from Earth below. Your weather from back home also stirs up this one-of-a-kind destination. Experience the unique beauty of every season, as changes in Earth's atmosphere, daily and annually, can create pressure waves, changing the ionosphere's shape and density. Venture to the equator, where our particles are packed in lush and thick. Cruise along a magnetic field line and see how the ionosphere's charged material also interacts with Earth's own magnetic field. Don't miss the superhighway of particles zipping out to space and back down to the planet. This unpredictable parade of charged particles can help you unplug and unwind. This is because the crowd of particles can garble the radio and satellite communications from home. The ionosphere welcomes you to discover more about this little-known region. After all, once you've explored this interface to space, who knows how much farther you'll be able to go.
And launch team, be advised, we have just gotten waypoint P recycle. Again, we lost comm in the last couple of minutes. We've switched our frequency comm to the L1011 to 133.80, and we're going to stick on that for the remainder of the operation. At this time, I would like to poll for concurrence for recommended action, recycle. Rock?
Rock concurs.
NGLD?
NGLD concurs.
And NLM?
NLM concurs.
We'll go for recycle. Check Alpha 25.
go for a recycle.
And Peg, verify power status.
LC Peg, Pegasus is on external power.
Okay, copy that, Peg. We'll check Romeo 2 complete.
As you heard, we are go for another launch attempt and are waiting for a new T0. We'll provide an update shortly. NASA's Ed Chris Gersh caught up with an ICON principal investigator, Thomas Emmel, to find out why it's important to study the ionosphere.
So, Tom, why do we want to study the ionosphere?
Well, that's a good question. So, the ionosphere is the densest plasma in space between us and the sun. And that plasma has a number of effects on systems that we use every day.
So the coolest part that I like about this particular mission is that you got to have an understanding not only of the Earth's weather, but also space weather, because they're really kind of combining, you know, in between the ionosphere. I mean, that must be really difficult or a challenge for you to kind of understand the ionosphere.
That's right. So space weather is a big topic, and when it stirs up the ionosphere, it's hard to maybe see other sources that are driving these changes in the ionosphere. But 95% of the time, space weather is pretty benign and quiet. We don't have a space hurricane every day. We do find that the conditions in the ionosphere are hard to predict anyway. We think that's probably because there's another mechanism driving the ionosphere, and we think it's the lower atmosphere, actually.
So when you have these storms coming towards the Earth, and you'll be able to make better predictions, let's say for GPS, for communication systems, because sometimes those will kind of get out of whack, or they actually can get damaged during a strong storm.
Well, there's three sort of effects, but some of the major effects are, like you said, are communications, because the ionosphere can get stirred up and become very variable, and then we generally use it to bounce signals off of all the time for long-range communications, and that can be adversely affected. Then there's geopositioning, as you noted, so those users aren't bouncing signals off the ionosphere, they're trying to penetrate the ionosphere from GPS satellites. And those signals can become scrambled as well, and that can affect everyone from people who are trying to drive a combine with a GPS to airlines. And then the third users focused on space weather are power and utilities. So all those currents that the utilities are worried about are currents that are driven because there's current overhead in the ionosphere. So being able to predict that condition in the ionosphere is key for those power operators as well.
Now, when we're talking about the ionosphere, what kind of range are we talking about in the atmosphere?
So that's a good question. So in the daytime, the ionosphere is about 100 kilometers up, or 62 miles. That's where the plasma starts. And it goes all the way up to a big peak about 300 kilometers. The nighttime, the lower ionosphere sort of disappears. It recombines. The sun's not driving anymore. But the upper ionosphere just sits there. And that's what you use to bounce signals off of at nighttime.
And so it's easier to communicate at night
That's right.
than it is during the daytime.
If you've listened to shortwave radio, you can get Radio Moscow or Radio Tehran in the middle of the night. You can't get that in the daytime.
You can't get it in the daytime. Now, Tom, as the principal investigator of this mission, what is your ultimate question that you want to answer?
What I want to understand is why the ionosphere is completely different one day to the next. And we've tried to model it. We don't have the measurements. You'd have to guess. And then maybe you're right or maybe you're wrong. Why is it doing that? So we've never had the data in the daytime and the complement of instruments at the same place at the same time to even approach that question.
Thanks to our NASA Edge friends for joining us. Now we're going to check back in with the Mission Director Center for an update. Joshua, Malcolm?
Sorry, we are recycling through the racetrack, so we're moving towards another launch attempt. We're getting word that should be at approximately 10 p.m. Eastern time. So we're hearing a lot of great chatter among the teams. You mentioned those 4 teams earlier this evening working together really well to be able to get back to the point when we can give this another shot tonight.
That's right, Josh. We've got a large number of checklists we need to work through among all 4 teams, and they're just demonstrating their ability to adapt to a new set of circumstances and work through their checklist and get us back into launch posture.
That's right. We want to give you a chance to see a little bit more about the Pegasus and some of the people involved in that. So our NASA's Daryl Nail caught up with Phil Joyce with Northrop Grumman to talk more about the Pegasus. Take a look.
Thank you, and hi everyone. We're here at the skid strip at the Cape Canaveral Air Force Station in Florida, and I'm joined by Phil Joyce, Vice President of Space Launch with Northrop Grumman. Behind us is the Stargazer and the Icon spacecraft. It's an exciting time to be here. It is launch day, 2 years in the making. How are you feeling personally about that?
Well, there's really no day like launch day. Everybody is just jazzed for this mission. It's been 2 years of hard work. And a lot of trials to get to this point. The team couldn't be more excited and more confident that we're going to have a good mission today.
Let's talk a little bit about the trials. There were some problems that were encountered that you had to overcome during that time. Talk about them and how you fixed it.
Yeah, well, on some previous launch attempts, we observed some anomalous readings in one of our position feedback sensors on the rudder. The rudder is on the top of the vehicle and is what steers the Pegasus during its first stage of flight. They were concerning enough to us and to NASA that we stood down and we did a very long and detailed investigation on the cause of those, determined what that cause was, made corrective actions, implemented those, and that got us to where we are today, ready to launch.
And where we are is standing right in front of the spacecraft and the plane as well. And you can hear our audience, probably the hum of those generators in the background. They're playing a key role ever since it got here and all the way up until launch day. It helps protect the spacecraft. How does it do that?
What you're looking at back there is our launch pad. The L-1011 is a flying launch pad as well as the first stage of our rocket. And those generators are required to operate those L-1011 systems like any normal commercial aircraft, but also to protect the spacecraft environment inside of the Pegasus fairing. This particular spacecraft, the Icon spacecraft, is very sensitive to contamination. And the systems that you hear in the background are providing a clean source of temperature-controlled air to that spacecraft so that we can ensure we have a great mission.
And I hear it's 65 degrees. I'd like some of that controlled air on me right now.
Yeah, it's a little warm out here.
It's a warm October day here in Florida. What are you looking most forward to, and where will you watch the launch?
Well, of course, we're always looking for a successful launch and a happy customer. That's what we're here for. I'll be in mission control with the rest of the Pegasus team, doing the countdown and being part of all of this.
Bill, thanks for joining us. We appreciate it. We'll send it back to you in the studio.
All right, so we still are live. You're now looking at the engine end or the motor end of the Pegasus rocket. So this is a camera mounted to the bottom of the L-1011. So Malcolm, I wanted to ask you, just thinking about the Pegasus, obviously we're doing a lot of work in the sky right now. What kind of things have to be done in preparation for this launch on the ground or in the sky?
Well, on the ground, starting with on the ground, we need to verify that the components of the system are responding to commands. So for a ground test, we'll move the elevons with external power and communication capability as well as ECS, verifying we can control the environment around the spacecraft. In the air, we will be verifying the hook release mechanism just to make sure that it's fully charged and ready to release Pegasus on command. Just as an example, and then obviously we are also coordinating comm channels and things of that nature. So all 4 teams are busy right now.
Yeah, it makes a ton of sense. Right now, again, we mentioned that because of just the speed of the plane, whether it be headwinds or tailwinds, we're now trending towards about a 10:01 estimated time to be inside the box. Again, that box being this space over the Atlantic Ocean, 40,000 feet off the ground, 10 miles wide, 40 miles long. So we're moving towards that. We want to actually show you a little bit more about the Pegasus and this launch in particular. So we've done a number of what we call T0 videos. Essentially, this is a series we've done with Launch Services Program missions, where it kind of takes an in-depth look at missions and kind of what all is involved. So take a look at this. This is essentially part 1, because part 2 will be obviously part of the launch.
Where does Earth's atmosphere end and space begin? In a mysterious region of space, scientists call the ionosphere, a volatile place, where terrestrial weather from below meets space weather from above. It's also where our astronauts and critical space assets orbit. Without a proper understanding of this dynamic region in space, the technology and communication we rely so heavily upon could be at risk. That's why NASA is launching the Ionospheric Connection Explorer, or ICON, to give us answers.
The primary goal of the mission is to gain an understanding between the weather here in our atmosphere and in the ionosphere and space. We don't quite have a handle on what's going on up there in the ionosphere, so this will give us an opportunity to understand that.
The ICON spacecraft only weighs 364 pounds, so NASA's Launch Services Program chose Northrop Grumman's Air-Launched Pegasus rocket to deliver it into a 360-mile-high orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
What's unique about the Pegasus rocket is that it is an air-launched vehicle, and that allows us to launch from anywhere in the world.
The challenge with processing Pegasus is that it's a flying solid rocket motor. Solid fuel ready to burn as soon as it's ignited.
PLT, LC is go for launch. PLT confirmed.
PLT confirms go for launch. LC, RTO, countdown net, liftoff, first function time.
It requires special attention. An explosion-proof processing facility at Vandenberg Air Force Base in California, where the spacecraft must be mated to the rocket and sealed inside its protective fairing. It's one of the few launch systems in the world where the payload is attached to the launch vehicle before it's encapsulated. Once complete, Pegasus is free to launch from anywhere in the world.
Once we've established that we're ready, we then transport our entire launch team and hardware to another part of the world so that we can insert ourselves into the proper trajectory.
But to get there, Pegasus still needs to be strapped to the belly of the L-1011 Stargazer. Strapping 55,000 pounds of solid rocket fuel to the bottom of an airplane is tricky, but these rocket scientists and engineers are up to the task. Once ICON and Pegasus are locked and loaded, then it's up to the pilots to fly the Stargazer into its drop zone.
Engine start 2.
So there you go, a little bit of the behind the scenes on this mission in particular with the Pegasus and ICON. Obviously, the next chapter in that story is hopefully going to be written tonight as we're coming around for our next attempt. There on screen, you see the racetrack that we're traveling. So again, we made it inside the box, but had communication issues, and so we called, an abort was called, and so they essentially meant they were going to recycle and run this racetrack. So they've literally just kind of circled around, more of an oval, but definitely circling around there, and headed back towards that box. And I want to kind of recap those the facts we hit earlier. Malcolm, can you tell us a little bit more about the Pegasus rocket itself?
Yeah, Pegasus is a little bit more than 57 feet long from nose to aft nozzle, 52,000 pounds of solid rocket propellant, and this will be our 44th launch. We're excited, ready to rock and roll.
And Malcolm, can you talk a little bit more about your personal experience? You actually have worked on some of the Pegasus missions, correct?
That's correct. Directly on the Cygnus mission and various other Pegasus missions over the years.
Very cool. So we're hearing lots of good chatter. There's essentially after the point when they were able to reset the clock, it looks like we are targeting right around 10 o'clock or so for our expected time to be inside that box to drop. So they're cycling through all of those same processes they did before. Again, it's a choreographed effort. It's something that everybody kind of knows, and literally they called out turn to this page. So everybody's on literally the same page proceeding through the launch countdown. And so we're going to come back up here in about 30 seconds on Omar Baez's NASA poll. So NASA launch manager Omar Baez, he's going to poll his team. We heard some good chatter from his team talking about making sure that their batteries are in good shape, everything's in good order. So let's listen in just a second, and we'll hear Omar's poll of his team.
And RCO, if we can get a reset of the clock at the L-7 minute call from the PLT.
RCO here, copy.
And this is DNLM with our Delta final launch readiness poll. NASA CE.
NASA CE is go.
SMA.
SMA is go.
SMD.
SMD is go.
NASA Mission Manager.
NASA Mission Manager go.
LSP.
LSP is go.
Copy. NASA team's ready.
All right, there we go. Malcolm, so on your screen you're seeing one of our control rooms here in this building. There are a number of these rooms like this with folks very diligently watching their screens, looking at data. How many people, roughly, Malcolm, do you think are really involved for hands-on tonight?
Hands-on in this building, probably on the order of 60 to 80 people. Everyone watching different systems and different areas of responsibility.
And there you go on your screen now. You see that's the tail end of the Pegasus rocket. This is a camera mounted to the bottom of the L-1011 Stargazer. So we will, once we do drop this rocket, essentially you'll just see that rocket kind of vanish from the view as it's released to fall downward for the ignition. So we are still tracking towards right about 10 p.m. Eastern time for our drop. Continue to hear lots of good chatter, a lot going on. Can you talk about the range a little bit, Malcolm? We talk about the range a lot because it's a big part of making sure we're good for a launch, but what's their role and how are they involved today?
So range safety is primarily responsible for public safety. They're constantly monitoring the position of Stargazer and Pegasus. And after drop, the range will be monitoring Pegasus to make sure it remains in a nominal launch path. And if it deviates, then they're prepared to take action to protect the public.
Yeah, that's so important to remember that they're really focused on public safety. And so obviously, like, we want our spacecraft to be in good shape, we want our rockets to be in good shape, but people are the priority. And we see that top to bottom all day, which is great. As we mentioned, we're working through all those countdown procedures, so we should hear Adam Lewis, launch conductor for Northrop Grumman, chime in here in just a second again to make sure he's polling all of the teams to make sure that we're good to go for a drop attempt number 2 tonight. Let's listen in.
5. Launch team at this time on a poll for final launch countdown. Rock?
This is Rock, clear to launch.
Peg?
Peg is go.
NGLD?
NGLD is go.
NLM?
NLM's go.
Launch team is going to proceed with final countdown at L-4.
All right, so once again there you see on screen our control room. That's actually the folks sitting behind us. Always happy to be hosted here in this space. Malcolm, I wanted to see actually if you could speak to the rocket a little bit. Because it's nighttime, you don't get a great chance to see this rocket and all that's involved there. But we have this expanded view of the Pegasus. We want to show you this on your left-hand side there. Can you tell us about some of the elements of this rocket?
Well, right off the bat, you'll see we have 3 stages, all solid fuel. And the most interesting piece is the first stage with the composite wing and the 3 fins, 2 elevons and 1 rudder. And these are used somewhat uniquely in the industry right now to steer the vehicle during first stage burn. We'll separate at the end of stage 1 burn, ignite second stage, and release the fairing burn for approximately another minute. Separate stage 2 from stage 3 and ignite stage 3.
So again, we're continuing to proceed through the countdown, hearing lots of good chatter, calls for moves to internal power, ensuring all the systems are communicating well. There again on screen, you see the back end of the Pegasus rocket, still targeting right around 10 o'clock for our expected drop time. I want to put up the racetrack again, just to again kind of show you where this plane is, flying very intentionally out there around the Atlantic Ocean. You can see the drop point is roughly 50 miles off the coast here. So there's 2 circles where you see PTRN. The smaller one is moving through the larger one. That smaller one indicates that's the plane's location. So we're getting very close to that drop box. Again, 40,000 feet off the ground, 10 miles wide, 40 miles long. And so proceeding towards that, we're going to be hearing these same calls again and again, which is great. Like these are all really important parts of the equation here. You've gotten to sit on console before, correct, Malcolm?
That's correct.
Can you talk about kind of the experience? Like, what's that like? Especially in a situation like this where you're recycling and there's a lot going on really fast. What's that feel like?
Well, it feels tense. You're watching your data. You're in an off-nominal situation already because you've aborted. But you're watching your system and reporting out. You're listening for the calming voice of the chief engineer or the launch conductor, and making sure that you're prepared to report out your subsystem status. So once you're in that situation, you really focus on all the practice sessions that you've had, and making sure that you're ready to rock and roll.
Yeah, obviously, our job is, there's definitely pressure here, but certainly it's different when you're back there because you're the ones making sure that this rocket's going to be safe and the spacecraft is going to get where it needs to be.
Absolutely.
There's people that have invested years of their lives, if not entire careers, on these science missions. So we're proud to be a part of this process. As we near our dropping point again, can you tell us, recap again for us the role of the pilot tonight?
So the role of the pilot is he's watching and flying his plane first of all, and he's also transporting Pegasus to the drop box, and will be responsible for final decision to release the vehicle and begin the powered flight for segment of our night tonight.
Sure. Let's see if we can toss up the tail end of that rocket again. I'm hoping that we might be able to catch. They do a fin sweep to make sure that mechanically things are working well. This is about the last time through the track that we lost communication, so definitely very anxious moments here. Again, in this final minute or so, still targeting about at 10 o'clock. I'm going to let you listen in and just kind of enjoy what's happening around us.
LC Peg, go for fin pin retract.
LPO, go for fin pin retract and fin sweep.
LC, Senior MEFCO, countdown L1011 is in the box.
Heading and ground speed are green. LC Peg, Peg is go for launch.
LC is go for launch, PLT confirm. Stand by. And drop on my mark. 3, 2, 1, drop.
Pegasus away. Vehicle is fully armed. Stage 1 ignition has been confirmed.
Launching Icon to explore and unlock the mysteries of the weather where Earth meets space.
Through transonic, power buses remain strong. Stage 1 fin actuator system is operating nominally and controlling the aerodynamic flight of the vehicle. Coming up on 30 seconds into the Icon mission. Vehicle has passed through max Q. Attitude remains nominal. All power buses nominal. All vehicle subsystems are operating as expected. Stage 1 burnout in approximately 20 seconds. Stage 1 has burned out. Attitude and the flight path are nominal. Approximately 10 seconds until Stage 1 separation. Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal. Stage 2 TVC is operating as expected to control the flight of the vehicle. Approximately 20 seconds until fairing jettison. Fairing deployment has been confirmed. Both halves have been separated. Vehicle attitude remains nominal after fairing separation. Power buses remain strong with excellent margin. Stage 2 motor burnout attitude remains nominal. At this point in the mission, the vehicle enters a long ballistic coast phase as it gains altitude, waiting for the proper time to ignite the Stage 3 motor. Good telemetry with S-band on Stage 3. We've got report from GNC that vehicle performance to this point is excellent. The vehicle flight computer is currently recalculating the proper time for Stage 3 ignition.
All right, so there we go. What you're seeing right now is actually an infrared camera that's based here at the Kennedy Space Center, and it's been able to track that. We didn't show you this earlier because there were clouds in the way. So as the rocket flew up above the clouds, we were able to get a picture of it. So we could even see the payload fairing separate and come off. So it is a really, really pretty night out. It's nice and beautiful, hearing lots of nominal calls, which is what we want to hear. I want to talk a little bit about ICON now, because as Pegasus will round out its job soon, ICON really does become the star of the show. So a few things. It has about the size and mass of a home refrigerator. It's deployed to about 27-degree inclination at 360 miles in altitude. So that's a little bit higher than the space station as far as its altitude is concerned. And the inclination is especially noteworthy because a lot of these kinds of science missions will have polar orbits, will then move from north to south pole. This one is flying much more equatorially. And it's going to be traveling at over 4 miles a second when it reaches its orbit. That's one orbit every 97 minutes, so roughly 16 orbits every day. That's the same speed just about as flying from Los Angeles to New York in about 12 minutes. So this thing is moving very quickly. I'm very excited for this. Continuing to hear those calls for nominal action, which is what we want to hear. I want to go ahead and actually toss this to an overview of the ICON mission in general. So go ahead and take a look now about this, some more about the science of ICON.
Up past the clouds, past the stratosphere, and even farther, some 60 to 600 miles above Earth, our atmosphere slowly gives way to space. This region, the ionosphere, is home to the aurora, but is also increasingly a key part of the human domain. It houses not only astronauts, but radio signals used to guide airplanes and ships, and many satellites. And yet, the ionosphere is not well understood. To explore this area of near-Earth space, NASA and UC Berkeley built the Ionospheric Connection Explorer, or ICON. ICON's task is to help us understand just what causes the constant changes we see in the ionosphere. The more we understand, the more we can protect our assets in space. From a position close to Earth, ICON samples variations in the ionosphere over the course of hours, days, and seasons. The mission will investigate how the ionosphere reacts to our planet's weather rising up from below, as well as space weather from above. A key set of the mission's observations focus on the most eye-catching phenomena visible in the ionosphere: airglow, colorful bands of plasma caused by solar radiation. ICON will use specialized technology to track how this plasma is moving through the ionosphere. As ICON learns more about the relationship linking Earth's atmosphere and the space environment, the information will help improve the ability to predict conditions in the ionosphere. One more important step in protecting ourselves as we venture farther and farther from home.
The reorientation maneuver for Stage 3 ignition has been complete, and the attitude of the vehicle is nominal. Stage 3 TVC is online. Stage 2 has been separated.
There you go. Some really great calls there. So we just heard that's the round out of the second stage finishing its job and the third stage beginning its task moving forward. It has a little over a minute to burn as the third stage.
The vehicle.
They're again a great nominal call on that. So everything proceeding well. We continue to hear great reports. The people here, you can feel the energy.
Operating nominally.
Everyone is really excited about this mission and having it on its way to where it needs to be.
Vehicle attitude remains nominal.
What you're seeing on screen is an animation with some data there on the right-hand side, kind of just tracking where this thing is right now on its way to its orbit.
Vehicle is now in orbit.
All right, a phenomenal call there.
Stage 3 burnout confirmation. Attitude remains nominal. Looks to be an on-target orbit for Icon.
Awesome. I'm joined now by Allison Powers, Pegasus business manager for Northrop Grumman. How does that feel to hear that call of, we're in orbit?
Wonderful.
We made it. We did
It's a great feeling.
It's been a long time, but it's great. Can you tell us a little bit about your role for Pegasus?
Yeah, I'm the business manager for Pegasus, which includes finance, new business opportunities, and just program control kind of roles.
Sure, that's great. So can you characterize kind of how has today's launch gone so far?
Well, one of our favorite words, as you mentioned, is using, that we use during launch is nominal. It might not sound very exciting, but in our world, it means that everything is looking good and on track. So right now, Pegasus is doing what is expected and doing good.
Perfect. So what's coming up next? What's kind of, because we're not done yet. We have a few more minutes to go here, but so what's coming up?
So what's coming up, we're in a coast phase. It lasts about 4.5 minutes. Stage 3 ignition is being computed real time by the vehicle onboard guidance system based on the flight so far. The stage 3 burn will last about 70 seconds. At burnout, the Pegasus rocket and Icon spacecraft will be traveling in excess of 17,000 miles per hour and have successfully achieved orbit. About 3 minutes later, payload separation will occur.
Awesome. So when payload separation occurs, that's the victory moment for Northrop Grumman, right?
Not necessarily. This is actually the 9th time that Pegasus has launched a Northrop Grumman built satellite. So when the Pegasus team's job is done, the Icon spacecraft team will kick in and start its mission.
So hopefully a little bit of a taking a breath to rejoice, but then obviously it's time to get back to work.
Right. Yep.
Pretty cool. Again, you're seeing on screen that animation. We said we were in a long coast phase. That's what you're seeing there now. So, Allison, what's next for Northrop Grumman? Obviously, it's been a big year for some other things going on with Northrop Grumman and aerospace. The Pegasus, obviously, this is great. So what's the future look like?
Yeah, so along with Pegasus, Northrop Grumman is actively working ground operations at KSC for our Omega rocket that's under development. We're currently modifying the mobile launch platform, one of them, and the vertical assembly building High Bay 2. Preparing for our launch at LC-39B in 2021. And cool fact, we're actually the first commercial company to utilize the historic vehicle assembly building.
Yeah, we're excited for all of our commercial partners, and Northrop Grumman definitely fits into that constellation for us. We're excited to have them there. Obviously, Northrop Grumman is... Clearly, they know what they're doing. We're here. We're on our way to orbit. We got a great spacecraft to work on. So, Allison, excited for you guys, excited for what's coming with Omega, and excited to see just the future of what you guys are doing. Brand new rockets are always fun.
Thanks. We're always excited to support NASA's critical space missions.
Allison, congratulations to you and the entire team. I'll let you go now and go celebrate a little bit.
Okay.
Once we get that spacecraft deployed successfully, solar arrays are out. So, thanks and congrats again.
Thank you, Josh.
phototelemetry in the center, waiting for confirmation of icon separation.
So I'm now joined by Steve Krein, Vice President of Civil and Commercial Satellites for Northrop Grumman. Steve, how you feeling?
Oh, feeling great. So far, so good. Everything, to use Allison's terminology, is nominal. So we're excited about that. And we're getting very close to separation of the what we call the observatory, which is the space vehicle built by Northrop Grumman, and the 4-instrument suite. So it's interesting, at launch, the observatory, there's a lot of inhibits that are actually enabled. We have inhibits on the, all the instruments are off. We have the main attitude control system, via the reaction wheels, torque bars, all the solar array release mechanisms, solar array drive, and all the transmitters are in inhibit, so we don't have any anomalous deployments or any spurious signals during the launch campaign. But at separation, then an autonomous sequence begins, and the transmitters actually start about 10 seconds after separation. We'll actually communicate with the TDRS network and start giving us telemetry. So we're looking forward to that. It's about to happen, and cross your fingers. All's nominal.
Yeah, it is kind of that. It feels like a cross your fingers moment, but ultimately, like, you guys are really experienced. You know what you're doing. So,
yeah,
I'm sure again with the last year and kind of the work that's been done, you guys have a high level of confidence that things will turn on like they should.
Yeah, exactly, and that's a very good point. That we had a longer delay than we would have liked before the launch, but we did go through a very I'll say very controlled, very disciplined recertification process. It's called comprehensive performance testing, where we exercise all the elements on the spacecraft and then did a full solar array deployment just to make sure that there'd be no issues when we came to this critical moment, which we're about to come upon. So again, a very high level of confidence, and all is nominal.
Awesome. And so, will you play an active role going forward in the science, as far as Northrop Grumman's concerned?
Well, certainly we'll be involved. We have a team right now out at the University of California, Berkeley, at the Mission Control Center to help with the initial certification. Following the release, as I mentioned, the transmitter will begin being enabled. The reaction wheels then and the torque bars will be enabled, and the spacecraft will stabilize. And then about a minute after release and separation, the solar array will begin to deploy, and it's a 5-panel array. So it's it takes a little bit of time. We want to make sure it's disciplined and controlled in its deployment.
Sure.
So it's about a 9-minute and 10-second deployment. But once that's out and rigidized and we acquire the sun, really the excitement for the day is over. And then we go into about a week-long process of just going through what I'll call the spacecraft bus certification to make sure everything's nominal, that everything's working as expected. And we fully anticipate that to be the case. And once that's done, then we'll start a 3-week period where the instruments are turned on in a sequential fashion. We verify that everything's nominal. And then finally, at about a month after separation, we start what's called science mode. And really that's the long-awaited period where we get the really high-value data back from the instrument and begin about a two-year process of really just collecting data and distributing to the science community to get the maximum utility for NASA, the science community, and for the nation.
Yeah. Steve, obviously there's so appreciative of the technical work that you all do.
Sure.
Again, congratulations on what's happened so far. Again, we have a few minutes left, but I'm going to let you get out of here and go kind of watch this thing kind of unfurl itself and just enjoy it with your team.
Thanks, Josh. It's a great moment, and look forward to mission success. Thank you very much. Yep.
All right, so we are listening closely for updates here as we proceed towards the solar array deployment. We're going to actually let you see a little bit more about the science and air glow.
The night sky is never truly dark. If you removed light pollution, the moon, stars, and galaxies, there would still be a very faint, colourful glow. That's air glow. With cameras, you can photograph it only on the darkest of nights. It's about 1/10 as bright as the combined light of all the stars. From above, it forms a luminous bubble encapsulating Earth. Appearing right at the interface to space, airglow holds clues to how our atmosphere affects weather in space, and how space weather affects humans on Earth. The bands of light span from 50 to 400 miles above Earth's surface. In the uppermost boundary of the atmosphere is the ionosphere. This is where our GPS signals and astronauts travel. What makes this region complicated is that it's constantly changing. It reacts to both energy emanating from the sun and weather near Earth's surface. And as the ionosphere fluctuates, so can conditions in near-Earth space where the space station lies. But spotting changes in the ionosphere is a lot like trying to watch the wind. You need a marker of some kind to see the invisible particles move past. And for that, we have airglow. These colourful lights reflect changes in the ionosphere, and this is due to the way it's formed. Our atmosphere consists mainly of nitrogen and oxygen, and small traces of other molecules. When these molecules reach the upper atmosphere, they're at the mercy of the sun. Ultraviolet radiation from sunlight excites them. They become energized and need to release that extra energy in some way. Atoms that remain energized long enough can emit that extra energy through light. In the lower atmosphere, we don't see as much light. The atmosphere there is dense. So when an atom becomes energized, there's a high chance it will bump into another atom and lose energy in that collision instead of emitting light. But as you travel further up, the atmosphere thins out. And like a game of dodgeball, the longer atoms stay untouched, the more time they have to emit a bright, colourful photon for us to see. That's why airglow is only seen in the upper atmosphere. But it can get even more complicated. Some collisions can produce light too. On the night side of Earth, green light is the brightest and occurs when oxygen atoms become excited through collisions with oxygen molecules. A variety of other complex reactions create red and blue light, as well as UV and infrared light that are invisible to the human eye. Each type of airglow contains information about the composition, temperature, and density of the upper atmosphere, all of which are key factors that can change dramatically and rapidly. So airglow turns out to be a fantastic proxy, illustrating not only how particles move through the ionosphere, but what kinds of particles even exist there, which is key information for helping us tease out how space and Earth's weather interconnect. And that's a great reason for NASA to study this beautiful phenomenon.
All right, I'm now here with NASA Launch Manager Omar Baez. Omar, congrats.
Thank you.
Does this one feel special, or is this just like another great launch for Launch Services Program?
It's another great launch for the Launch Services Program, but an awesome and great one. This one's been a long time in coming. We had some setbacks early on, middle of last year, and I'm glad that we were able to get this payload up in orbit and in a safe condition. We did confirm separation through the spacecraft TDRS link. The orbits look fantastic, and currently they're power positive, so everything looks fantastic for us. And wonderful Pegasus launch, and like always, when your launch pad is moving at 500-600 miles an hour, things happen, and this time the first attempt got us because we lost positive communication with the aircraft and the ground, and our rule is to abort the flight, go back around and try it again. And we did this once before during the HESI mission back in 2003, and were able to execute it flawlessly today.
Does that cause any additional anxiety among the team when you kind of have to racetrack like that?
I don't know about anxiety. This is a fun launch. It's in my operational function. This is about as good as it gets, and we enjoy it. The anxiety level is higher, the adrenaline's flowing, but what a cool way to fly.
Yeah, absolutely. So thinking about Launch Services Program, obviously this is the name of the game for you guys. What's next? What's coming up?
The next mission for us is the Solar Orbiter mission, which is, or SOLO. It's a cooperative with our partners from the European Space Agency, and it's another Helio mission. So interested in looking at the sun with that one, and we hope to launch it in early February.
Awesome. Will you be the launch manager for that one?
That will be Tim Dunn.
Okay. And your next mission is?
And I will be working Mars 2020 this summer.
Which is also super high profile. Obviously, we'll get there when we get there.
Yep.
We've got Solo to go first.
Yep.
But again, a big congratulations to you, Omar, to the entire team. Thanks for joining me. Appreciate you. Also, big thanks to Malcolm Boston for joining me riding shotgun as my co-commentator. So for tonight, from Hangar AE, that's going to be all. Jennifer, back over to you.
Thanks, Joshua, and thank you for joining us. For more on the mission, please visit nasa.gov/icon. In the meantime, we'll leave you with a replay of this evening's launch. From all of us here at NASA, thank you and have a great night.
1, drop. Pegasus away. Vehicle is fully armed. Stage 1 ignition has been confirmed.
Launching Icon to explore and unlock the mysteries of the weather where Earth meets space.
Through transonic, power buses remain strong. Stage 1 fin actuator system is operating nominally and controlling the aerodynamic flight of the vehicle. Coming up on 30 seconds into the Icon mission.